Hi, I'm Professor Goins and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, you're in the right spot, so go ahead and click the subscribe button. That said, let's get into the current video. In this video, I want to talk about the integrating factor, which is a solution technique that you will learn in your introductory differential equations class. And more than likely, this is going to be the very first example of a solution technique that you will learn in that class. Let's see how this works. Once I have a differential equation of the following form, y prime plus p of t, y is equal to q of t. So once my differential equation is in that particular form, we can use what's called an integrating factor, which is given by the following. The Greek letter mu is equal to e to the integral of p of t dt. So notice that the integrand there is the coefficient of y in the differential equation. Okay, so for this particular differential equation, let's compute the integrating factor. Mu is e to the integral of 3 over t dt. Okay, so let's go ahead and compute that. Well, integration is linear, so I'm going to take that constant and I'm going to pull it out front of the integral. So e to the 3 integral 1 over t dt. Okay, antiderivative of 1 over t, of course, is the natural log. So this is e to the 3 natural log of t. Yes, there is an arbitrary constant of integration, but notice if I put a plus c here, then I could rewrite this as e to the c times e to the 3 log t, and the e to the c is just an arbitrary constant factor, so we're just going to ignore that for the moment. All right, now natural exponential, natural logarithmic function are inverses, therefore their composition would cancel. However, I do have this 3 in between there, so let's move it. Coefficient of a logarithm can be moved on the inside. So this is e to the natural log of t cubed. Now, consecutive operations of inverse functions cancel, leaving me with t to the third. Okay. Once I have my integrating factor, what I do is I multiply the original differential equation by that, which gives me the following. T to the third times the derivative dy dt plus t to the third times 3y over t, yes, that will reduce, we'll reduce that here in a moment, is equal to t to the third times e to the t over t to the third. Now let's go ahead and reduce a couple of those terms, meaning this one and this one. T to the third times the derivative plus 3t squared times y is equal to e to the t. Now, that perhaps doesn't look any simpler than the original equation. However, this is in a very special form. Notice what I have here. I've got the sum of two terms, right? And within those terms, notice I've got a y, and over here I've got its derivative. And then here I've got t cubed, and there I've got its derivative. Well, the sum of two terms, where I've got like terms and derivatives on opposite terms there, should remind you of one of your differentiation rules, meaning the product rule, right? So this is actually the same thing as the derivative of, so let's see if you can fill in the blank there. What did I differentiate to get this? What did I use the product rule on to get this? Well, notice I've got t cubed and a 3t squared. So this is the derivative of that. This is the derivative of that. So what are the two terms that don't have derivatives? T cubed and y. So t cubed times y inside the brackets there, use the product rule on those two terms, this term, and I get what I have directly up above. And then this is equal to e to the t. Now, every time you use an integrating factor to solve one of these linear first-order differential equations, you're going to get some sort of an expression like this, where I've got the sum of two terms. And every time, it's going to be the derivative of a product. Well, you might be thinking, how am I going to come up with that? Like that seemed like maybe it was okay in this case, or maybe it wasn't. I don't know. So the way we actually do this, there's a shortcut, right? T cubed, where did that come from? That was the integrating factor. Y, that's the unknown function. So actually every time, this is going to be inside the brackets here. mu y. It's always going to be the derivative of the integrating factor times the unknown function every single time. Okay? Well, now, I want to solve for y, right? When I solve a differential equation, the goal is to solve for the unknown function. The only place where y occurs is right here, so what I have to do is get rid of both the t cubed and the derivative. Well, I have to get rid of the derivative first, meaning antiderivative of both sides. So that says that t to the third times y is equal to the integral of e to the t dt. So therefore t cubed y is e to the t plus an unknown constant, or arbitrary constant. Now, finally, solve for y by dividing by t cubed, and I get y is equal to e to the t over t cubed plus c over t cubed. And this works for any constant c. That function would then be a solution to this original differential equation. Okay? So once again, let me just run through the procedure overall really quickly here. Once I have my differential equation in this form, first derivative plus a function times y equals another function. Okay? So I've got my first order linear differential equation where the coefficient of y prime is 1. Find my integrating factor. It's e to the integral of the coefficient of y, so e to the integral of p of t dt. Integrate that, and then simplify as much as I possibly can, depending on what you get. Multiply the original differential equation by the integrating factor. The left-hand side is then going to be a derivative of a product. It's actually the derivative of the integrating factor times the unknown function, again, every single time. There. I'm going to integrate to get rid of this derivative, and then I have to integrate this side. Now, depending on what this function is, you might have to use, u substitution, integrating by parts, partial fractions, whatever the case may be, whatever you have over here. So I compute that integral, and then the last thing I have to do is isolate y by dividing by whatever this coefficient is. And that is the integration technique, or the differential equation solution technique known as an integrating factor. And notice that really it boiled down to two integrals, right? So two Calc 2 or even Calc 1 skills. Anyway, thank you for watching, and please consider subscribing.